Hi everyone, let's solve today's daily challenge, that is jump game second. In this question, you are given a zero indexed array of integers nums of length n and you are initially positioned at nums 0, that is the starting index, and each element nums of I represents the maximum length of a forward jump from index I. In other words, if you are at nums of I, you can jump to any nums of I plus j, where j should be between 0 and nums of I, and I plus j should be less than n, and we have to return the minimum number of jumps to reach nums of n minus 1. So let's see what the question is. Let's consider the first case only, that is given to us in the question, that is 2, 3, 1, 1 and 4. So now what we have to do is, we are initially positioned at the starting index, that is the 0th index, and we have to take some jumps and we have to reach towards the last index, right? So now let's see how we have to take those jumps. So basically in the question it is given that we have these integers at each and every index. So these integers represent the maximum number of jumps that we can take from this particular index. So for example, if when we are at 0th index, the integer that we have is 2. That means we can make maximum number of 2 jumps, right, from this index to other indexes, right? So that means we can make 1 jump or 2 jump, right? So that is, we can jump from this index to this index or 2 indexes ahead, and that is the maximum number of jumps that we can take from this position. Similarly, when we come to 3 at this index, from this index the maximum number of jumps that we can take is 3. So we have choices 1, 2, 3, right? So we can make 1 jump, okay, wait, 1 jump from this index, or 2 jumps from this index, or 3 jumps from this index, right? 3 is the maximum number. We cannot make any more jumps than 3. So these are the maximum number of jumps that we can, these integers represents the maximum number of jumps that we can take from that particular index. So doing that, we have to reach this last index, right? We have to reach towards the last index, and what we have to do is, from this starting index we have to calculate the minimum number of jumps that we can make from this particular index, right? So let's see, for this test case, what will be the minimum number of jumps, right? From 2, if we see, we can make 1 jump or 2 jumps, right? So if we make 2 jumps, we will be coming here, right, at 1, and from here the maximum jump we can make are 1 only, right? So but we can see that we have a 3 here, right? And from 3 we can make 3 jumps at max, right? So if we make 1 jump, that will be a better choice, right? So 1 jump we will make here, and from 3 we have 3 choices, right? 1, 2, 3. So which one is the most feasible? So if you see, if you make 3 jumps, we will directly reach the last index, right? So that means 1 and 2. So we made a total of 2 jumps to reach the last index from the starting index. And if you see, out of all the other ways, right, these are the minimum number of jumps that we'll be getting, right? One way is also to, jump from here and then from here to here, right? There are multiple ways, but we have to calculate the minimum number of jumps out of all these ways, right? So let's see how we'll be solving it. So one thing that you can see here is that we have to consider all these possibilities, right? We have to consider all of these possibilities, that is from a particular index, right? For example, if we had 2, we had 1 and 2. These were the choices. From 3, the number of jumps we can make are these, right? From here we can make only 1, and from here we can make only 1. But from this index, because this is the last index, we don't have to make any jumps, right? So from this index we have to make 0 jumps only. Now let's consider the second case, that is 2, 3, 0, 1, 4, right? So if we have 2, 3, 0 and 1, 4, right? So let's see what are the choices that we'll have. So we'll be having for this 1 and 2, for this 1, 2 and 3, then from here 0, then from here one choice we can make, we can do, and this is the last index. So again we have to make 0 number of jumps. So one thing that you can see here is that this part, right, it's kind of a base case, isn't it? Right? So because we have to consider all these choices, so, and we also have a base case, right? When we reach the last index, we have to make 0 number of 0 number of jumps, right? So can we do a recursive function here, right? Definitely we can do that, right? Because that is one way to do it, right? We are at 2, right? So from here we have 2 choices, so we can create a recursion tree here, right? So out of these 2 choices, so what we'll be doing is we will be first traversing inside of this array, and inside of this array we will be considering this integer, right? Let's call it k. So when k is 2, so we will be having choices as 1 and 2, right? K choices we will be having, and we will be traversing in those k choices. And what we will do, we can simply call, let's say we store inside of a answer variable the minimum number of jumps, so we can simply call what minimum of this answer, and we can make a recursive call to the remaining array and to the remaining number of jumps that we can make, right? That is, we can make 2 jumps then, or for 1 jump, right? So we are saying that if we make 1 jump from here, then we will reach here. Then after reaching here, we will be considering all these 3 choices, right? So we will be making recursive calls to these, and after this we will be storing our answer inside of this answer variable. And what will be the base case of our recursion? When our n, right, when our n will be, when our I, right, will be equal to the last index, right, then we have to return 0. That will be the base case for this recursion. So this is the recursive function, right, that we can write. Now if you see the time complexity, definitely, because we are considering, like, we have the nums I, right, that the integer at an ith position is less than equal to 1000, right, and also the nums length is less than equal to 10 raised power 4. So at like in the worst case, what we'll be having is, just a minute, let me clear this all a little bit. In the worst case, what it will be like, in the worst case, it will be like we have an integer here, let's say we have 1000 here, so we have how many choices? 1, 2, and up to 1000 choices we will be having, right? Let's say we have an array with 1000 choices and its length is 10 raised power 4. So there will be a lot of calls, and this will definitely give us TLE. Now how can we optimize it? So whenever we have a recursion, right, can we memoize it? Right, let's see how we'll be memoizing it. Let me take another case here. Let me write some other integers here only. So let's say we have here 2, 3, 1, and let's say 5 and 2, right? We have something like this. So let's say from here, if we start doing the recursion, we will reach here, right? And if we take 1 jump, where will we reach? At 3. So we will have 3 here. If we take 2 jumps, where will we reach? This 1, right? Then from 3, the choices are 1, 2, and 3, right? And from this one, we only have 1 choice. So when we will be having these choices, then if we take 1, right? If we take 1 jump from 1, we will be reaching at this one. Okay. And when we will be taking or 2 jumps, then we will be reaching at this particular one. Okay. And when we will be doing if we will be taking 3 jumps, right, we will be reaching this 4. Okay, then okay, so let's see, after this one we will be reaching another 4. So this 4, we have how many choices? 4 choices. Now for all of these choices, right, for all of these choices, we will be calculating this again and again, right? This is the common part. This thing that you can see is a common part for all these values, right? We will be considering this plus these, right? So if I am saying, if I take 4, from 4 if I am considering, then I have to consider this part, right? This will be common, and then I will be adding this, right, the jumps for this call. So definitely we will be doing multiple calls, so we can memorize this thing, right? We can calculate this thing only once, and we can store it somewhere, and then we will be, moving forward. So this is what memoization. So after memoization, you can write a DP approach. So let me just quickly show you the code. Okay, so here's the code for it. So in here, what we are doing is we are creating a DP array, right? Inside of this, we are this is for the jumps, right? The minimum number of jumps for particular index. That is what we are calculating for a particular n, right? And DP of 0 is 0. Why? Because let's say your array length is 1 only. Okay, if your array length is 1, then definitely you're standing at the last index only, so you don't have to make any jumps. So that is why dp of 0 will be 0. Then as I said, what we'll be doing is we will be traversing inside of this loop, right? That is the array. And then we will be considering each and every integer in that particular position, and we'll be traversing in that. And then what we'll be calculating is the minimum number that we can get out of all these choices, right? So let's say if we have this, right? If we have 2, so from 2 we have 2 choices, right? We have 1 and 2, right? So what we will do, we will calculate for these choices the minimum jumps that we require, right? So from here, okay, first we will go here, right? Then here what will be the choices 1 2 3, and then as we said we will move here. Okay, so when we are at 4, what are the choices that we have? So for 3 we will be considering how many choices? These are the 3 choices, right? For 2, these are the 2 choices. So out of these, whichever is giving us the minimum number of jumps, that is what we are storing inside of this dpi plus j. So in this loop we will be considering which choice we are taking, and we are storing the number of jumps to reach to that choice. So after this we will simply return dp of n minus 1, that is the last index, right? By reaching the last index, what are the minimum number of jumps that we made? So this is the DP approach. Now let's see an optimized approach of it. If you see, this approach will run in O of n square. Why? Because not in O of n square, but it will still be taking, like this will pass. If you try to use this DP approach, it will pass. But as we said, the integer can be anywhere between 0 to 1000, right? These integers, and the length of the array is 10 raised power 4. So it's O of n into k actually, right? So this DP approach, and also we are using an O of n for storing this DP array, right? So this is the space. But let's see, can we optimize it? Can we reduce the space to O1, and can we reduce this time complexity to O of n? So let's see the approach for that. Okay, so this question can also be solved using greedy approach. Let's see how. Okay, let me just remove this. Okay, now it's removed. So let me also take the previous case only, so that will be more clear to you. Now let's see one other approach. Now what we are doing is we are simply considering this value, right? And from this value, what are the choices? 1 and 2. Okay, so basically from here I have these 2 choices, right? I can make jump to this or to this value. Okay, so okay, now so what we will be doing is we will be taking 3 variables, right? First will be for the jumps. Okay, the second will be for the current index that we are at. Let's call it current end, and then we will be having a current far. Okay, these are the 3 values that we will be having. Okay, now let's see what these 3 values are. So this current far is nothing but we will be calculating current far at each iteration, and it will be equal to that particular index plus whatever value we have at that particular index, that is nums of I. So we will be calculating this current far with this. Okay, now let's see. So let me write these indexes also here. So we have this. So for this position, what is the value for current far? It is 2. Okay, now we have these 2 choices. So when we have these 2 choices, what we'll be doing is we will be updating this current far. So here it will be 4 and here it will be 3, right? So which one is better? Which one is better? Because if you do 1 plus 3, so what does this 4 signify? That is, you will be reaching this index 4, right? This is what this I plus nums I is signifying, right? So you will be reaching at this position, right? So this is what this means, right? This is the index that you will be reaching after you add these 2 numbers, right? Similarly, if you add if you add 2 and 1 here, so you will reach 3 index, right? So let's see that in action. So we have 2, 3, right? So what you are doing is, from this index, if you make from second index, if you make one jump, where will you reach? The third index, right? So this is what I plus num size signify. That is the index that you will be reaching, right, after jumping from there. So we will be storing this current var, and whenever this current var, like when we will be, exhausting the choices of this, where will we exhaust its choices? When our ith index will be equal to this particular value, right? When our ith index will be equal to current end, we will be exhausting these choices. How? Here the current end was 2, right? So we will be exhausting our choices at the second index. Okay, similarly, let's do for the next iteration. Let's see. Let's do the similar thing for this 3. Right. Now when we will be at this 3 position, right? At this 3, the value of the farthest is current far is 4. Sorry, this will be current end. Okay, this is 4. So we will be breaking out of this loop when this current 4. Okay, let me take another case, because at current 4 we will be actually at the last position, right? So we will be getting an answer. Let me take another case. Let me raise this. Let's say we have an array like 1, 2, 1, 4, 3, 2, and 1, and 5. Let's say we have something like this. Now let's start. Okay, wait. Let me take this as 3 only. Okay. Now let's see. So what do we have to maintain? 3 variables. What is the first variable? That is our current end, which will be initially this position, right? Current end will contain I plus this particular position. That is 0 in this case, right? Oh, sorry, it is 3, right? That is 0 plus 3, which is 3. Okay, so for this we have to consider these 3 steps, right? So let me write indexes here. Oh, wait, this is 5, 6, and 7. Okay, so we'll be considering these 3 choices. From 3, where can we make the jumps? We'll be making jumps at 1, 2, and 3, right? So our current end is 3. Now we will be updating current var at each position, right? Current var, when current end is 3, current var will be, this is 3, this is also 3, but this is 7. So which is better? 7 is better, right? So our current var will become 7. So that means if we make jump to this position, that will be giving us minimum jumps, right? Why? Because if you make jumps here, we will be only going to third index. But if you make jump from 3 to this position, you will be going directly to 7th index, right? So that is why we are taking current var. So when you will be exhausting these values, you will be iterating here, right? You will be calculating current var at each iteration. When your current var will become equal to current end, right? Then what we will do is, you will update this current end. Sorry, when your ith position will become equal to this current, that ith position will become equal to this current end, then you will be doing what? You will be updating this current end to current var, and you will be making a jump. Okay, you will be making a jump, and you will keep doing until you will reach this position. That is the last index, right? And after that you have to break out of the loop, and that will be your answer. So let's see, let's code it. So what I am saying is, we will be having 3 variables, that is the jump count, and we will be having a current end, which will be initially 0, and we will be having a current var, which will also be 0. So current var is nothing but it is calculating the optimal choice for us. As we saw here, from 3, what is the optimal choice? From 3, the optimal choice is to make 3 jumps from this index. So that will be, taking us to the 7th index after we make this jump. right? So that is this, that is the last index. So what are the jumps are equal to 2, right? Those are the minimum number of jumps. So let's see, our current var will be 0. Now what we'll be doing is we will be iterating inside of this array, that is I is equal to 0, I less than nums dot size and I plus plus. Now what we will be doing is we will be updating our current var at each iteration, right? So current var is nothing but current var is equal to maximum of let me put it inside of this function, current var, that is its previous value, and I plus nums of I. This is our optimal value or optimal jump that we will be getting. And after we reach to this index I, which will be equal to the current end, right, which will be equal to the current end, then what will happen is we have to and also we have to check, right, that this I plus the jumps that we will be making, okay, that is the jumps that we will be making is I plus j we will be checking, right, I plus nums of I, it should also be less than n, okay. We will be checking this condition, and then what we'll be doing is at this point we will be updating our current end to the current var, and we will also do jumps plus plus. And after this loop we will simply return the value of the jumps that we will make. So these will be the minimum number of jumps that we will be making. So let's quickly run it. Okay, this is and oh, okay, I haven't stored it anywhere, so nums dot size it will be. Okay, so this is what we'll be doing. So I hope you have understood the problem, and this approach is in O of n complexity, right, time complexity, and O of 1 space, because we are not using any vectors. These are just variables that we are using. So it is of O n complexity, time complexity, and O1 space complexity.